After you read the problem very carefully, my advice to you is to highlight the original claim that you're trying to test. So here we're trying to test the claim that the average weight gain for all college students is 15 pounds. Then once you know what that claim is, go ahead and write down the parameter that we are testing. So the parameter is a mean value, where this represents the mean weight gain, right, of all freshman students. So we're talking about the population here. Okay, once I've written that down and identify what mu is, I'm going to go ahead and take what I highlighted and convert that into symbolic form. So the claim that we're testing, so I'm going to put it in quotations here, is that mu is 15 pounds, okay? And then keep track that this is the original claim. Now, notice that this claim that I've written in symbolic form has the equal sign in it. So that's an indication that when I do the hypothesis test, I'll go ahead and write it down as a series of 5 steps, where the first step is to write our null and our alternative hypotheses. This is an indication that the null hypothesis is the claim that is the original claim. So again, keep track of that. And then we go, well, what if that is not true? Then the alternative is that the average weight gain is not 15 pounds. This also lets us know that we have a two-tailed test. What I mean by that is on the bell-shaped curve here, we assume that students gain on average 15 pounds. So if this is true, then every time I take a random sample of 125 college students and calculate the average weight gain, it should be 15 pounds. Again, if I repeat that study, right, if this claim is true, then again, I should expect my sample mean to be 15 pounds. And that should occur at a high frequency if I keep repeating my study. And if it's not 15 pounds, then maybe it's a little bit higher than 15 pounds or a little bit less than 15 pounds, but it shouldn't be that far off from 15 pounds. But if this claim is not true, then we will see that we will not get a sample mean anywhere close to 15. So in this study, notice that the sample mean is 2.7 pounds, which your gut feeling is probably telling you that, oof, this is nowhere close to 15 pounds. But I need to confirm that it's actually really far away from 15 pounds. So if I exaggerate my tails here, I hope that you would agree with me that an X bar of 2.7 pounds is going to be really far away from 15, okay? Real quickly here, we're using a significance level of 0.05. Because I have the not equal sign, this means that I have a two-tailed test, which defines my critical region in the left tail and the right tail, where half of alpha is going to be on the left and the other half of alpha is going to be on the right. If you use now, before I start using the calculator, I need to ask myself if I'm going to use the normal distribution or the t-distribution. So here, notice that nowhere in the problem do we know the population standard deviation sigma. So because this is unknown, this lets me know that I'm going to use a t-distribution. And with t-distributions, I need to know my degrees of freedom. So here, that's n-1, or a degrees of freedom of 124. So going to the calculator, if I use inverse t, I'll be able to find my critical value. So the critical value is the t-score that separates the red area on the left and the red area on the right, which is called our critical region. So real quickly, I went ahead and did this on my calculator. And this gives me a critical value of negative 1.98 on the left and positive 1.98 on the right. So that is the critical value that defines the critical region. Okay, second step is we've got our sample data here where our sample mean is 2.7 pounds. I need to calculate my test statistic that corresponds to that sample mean value of 2.7 pounds. You can use the formula x bar minus mu naught, where mu naught is that 15 pounds. Divide that by your sample standard deviation over the square root of n. So if you put all those numbers into your calculator, 2.7 minus 15 divided by 6.4 over the square root of 125, that will give you a test statistic value of negative 21.49. I'm going to box this in green, right? This test statistic, notice, is much greater than 2 standard deviations below the mean. So at the center here, your t-score is 0. This t-score, right, is negative 21.49. It corresponds to the t-value for an x-bar value of 2.76. So right here, I'm going to mark it. It's not to scale. It should be much further to the left, but you can see here that that's really far away from 0. On the left of this value that I'm shading in green, that is half of your p-value. The other half is going to lie on the right side where that marking there would be positive 21.49, okay? So the third step in a hypothesis test is to calculate that p-value. The p-value is a probability, so it should always be a number between 0 and 1. So if you ever get a p-value that is a number bigger than 1, that means that either 1, you did the problem wrong, or 2, you didn't read the number correctly given to you in the calculator. Okay, so our p-value here, I'm going to actually use my calculator function. So on your calculator, I'm writing on the right here in red, you're going to do a t-test. The reason why we're doing a t-test is because we're using the t-distribution. We're testing a claim about a mean value, and we don't know the population standard deviation. The t-test is going to ask you to put in mu naught, which is 15, and then it's going to ask you to put in all of your sample data. So you're going to type in x bar, your sample standard deviation value, and then make sure that the alternative hypothesis matches up with the alternative hypothesis that you wrote in step 1. So make sure you choose the correct symbol, which is the not equal symbol. And then when you do that, the calculator will confirm that your test statistic, right, your t-value is negative 21.49, and it will also give you a p-value. I'm going to write the p-value in green down below here. It's going to give you a number like this, 1.262847 e to the negative 43. Notice that 1.26 is a number bigger than 1. Obviously, our p-value cannot be a number bigger than 1. So this is your calculator telling you that you have a number that's written in scientific notation. 1.2628 is really 0.000, and I can't write all the zeros because there are 42 of them, 42 zeros before the number 1262884 shows up. I hope you can see that this p-value is basically 0. So we have a p-value of 0. So the chances of getting a test statistic of negative 21.49 or an X bar value of 2.7 pounds or something more extreme than that is basically 0%. Okay, if you take a look at my drawing of that bell-shaped curve here, I hope you can see visually that the p-value, the area shaded in green, is smaller or less than our significance level, which is the area shaded in red. So that helps us make a decision in step 4. In step 4, we're going to make a decision about your null hypothesis claim. So make a decision about HO. So here, I'm going to use the p-value method. You are welcome to use the critical value method, but I'm going to use the p-value method. So the p-value method says compare the p-value of 0 to your significance level of 0.05. And notice that since the p-value is, so here, I'm running out of space here. Since the p-value, and make sure you write down that p-value, 0, is less than your significance level. Again, write that down, is less than 0.05, right? We will reject the null hypothesis claim. Okay, all right, now we need to actually state our conclusion and write this all down so that it actually makes sense for any person reading the conclusion, all right? Because when you say the p-value is less than the significance value, we reject the null hypothesis, what on earth does that really mean? What it means is this. It means that there, okay, is sufficient evidence at the 0.05 level, okay, to reject the claim that all freshman students, okay, gain 15 pounds on average. Okay, so basically you're saying that claim is not true. And you can stop there. That is a perfectly good conclusion. But if you wanted to add a little bit more detail, you can say, in fact, the data suggests that the average weight gain is less than 15 pounds, most likely closer to about 3 pounds. Okay.